Next, we will take a look at random variable generation. We will see inverse transform sampling, accept-reject methods, including the envelope AR, ratio of uniforms, and then we will finish with some examples. In general, if we want to generate a random vector from any arbitrary distribution in a Euclidean space, we will have the following two steps. First, we will need to draw uniform random numbers, which we discussed in chapter 1, so we have seen methods to draw or to create random uniform numbers. And then we have to apply a function g on those uniform random numbers in order to obtain the random vector x that comes from the wanted distribution. In this chapter, we will review a number of various generic implementations of the second step. Specific examples are held for the exercises. The methods that we will discuss here are exact methods. They are exact in the sense that each generated random variable will exactly follow the required distribution. Approximate generation methods, such as Markov chain Monte Carlo, will not be discussed here. So for this chapter, we will make two assumptions. First of all, we are able to create perfectly IID uniform variables. And secondly, we will assume that our computer has an infinite precision. The first method of random variable generation that we will see, namely inverse transform sampling, is based on this lemma. This representation lemma by Skorokhod tells us that if we have a cumulative distribution function f, and we have its generalized inverse, so f minus 1, which is basically the quantile function for the distribution, then if we apply this generalized inverse to a uniform random variable, then this f minus 1 of u follows distribution f. Thus, the generation of any sequence of random variables can be formally implemented through a uniform generator. This means, at least theoretically, that we can obtain a random variable from any desired distribution if we apply its quantile function to a uniformly distributed variable. Or, otherwise put, once we can generate an acceptably uniform sample, then from a theoretical point, we can use this representation lemma to generate a sample which will acceptably mimic the desired distribution. So the algorithm is very simple. We start by generating uniform random variables, and then on those random variables we apply the inverse, so we apply the quantile function of the desired distribution, and the values that we obtain that way, they will follow the desired distribution. Let's take, for example, the exponential distribution. For this distribution, we know the cumulative distribution function. This is 1 minus e to the power minus lambda x. And if not known, we can easily calculate the inverse function as well. We then apply this inverse function to a random variable u, which follows a uniform distribution, and then we know that this f minus 1 of u follows an exponential distribution. However, if u follows a uniform distribution on the interval 0, 1, then 1 minus u will do the same. So 1 minus u is also uniformly distributed on 0, 1, and so it suffices to take the minus logarithm of u over lambda instead of minus logarithm 1 minus u over lambda, because 1 minus u and u, they both follow the same distribution. The implementation in R then looks like this. First we set n to 100,000, so we will generate a sample of size 100,000. We generate 100,000 uniformly distributed numbers, and then we apply minus the logarithm to these numbers to obtain a variable x, a sequence of 100,000 values x, which follow an exponential distribution. So in this algorithm, we just took negative logarithm, so we divided by 1. It means that the parameter of my exponential distribution, so the value for lambda, is equal to 1. Furthermore, this algorithm also works for discrete distributions. In that case, it takes a little more work to find the generalized inverse, so to find the quantile function, but the global ID is the same. So what you have to do is find the smallest positive integer, k, such that f of xk is at least u, and then return xk. Let's make this algorithm clear on an example. Assume we have 5 possible outcomes and define the probability for each of the outcomes. So the first outcome has probability of 20%, the second outcome 30%, 10% for the third outcome, 5% for the fourth outcome, and 35% for the fifth outcome. We then set again the sample size n, and we create a vector of size n with all zeros. And then in the following step, we will fill in the vector x. We will fill it in with a random outcome, randomly chosen among 1, 2, 3, 4, and 5, and following the given probabilities for each of the outcomes. So how does it work? We need to know the cumulative distribution function, so we need to find the cumulative probabilities for the different outcomes. That's why we use cum sum of p. So this will return a vector 0.2, 0.5, 0.6, 0.65, and 1. So a vector of the cumulative probabilities for the outcomes. We then random sample a uniform number. The values of this random number are uniformly distributed in 0, 1. And then we will check what this number is and compare it to the cumulative distribution function. So let's say that we have generated 0.47. This 0.47 is the value for u. And then we have to compare this value with the cumulative distribution function. So we know that the quantile is the smallest positive integer, such that f of x is larger than this u. So we compare it, we see that 0.47, this one is smaller than 0.6, 0.65, and 1. So applying the function which to this comparison will return a vector 3, 4, 5 for the outcomes for which that the probability is larger than the generated number. And then we know that the quantile is the smallest positive integer, which is larger. So we take the minimum of this vector and we return 3. So in this specific case, the quantile, the smallest number, the smallest outcome for which the cumulative probability is larger than this uniform number, this will be 3. And this way we fill up the entire vector x with random numbers sampled from 1, 2, 3, 4, and 5. And if you look at it, if you execute this code, you will see that the probabilities, the frequencies of those numbers in the vector x, they correspond very well to the predefined probabilities. So as we said before, using the representation theorem, we can theoretically generate a sample of any distribution. However, in practice, this approach is only applicable when we can explicitly define the cumulative distribution function. So if we are not able to calculate the generalized inverse analytically, so if we are not able to find a closed formulation for this, we cannot apply this algorithm for random variable generation. In that case, what we can try to do is find a numerical approximation of the cumulative distribution function and the quantile function. Because of this remark, the algorithm, so the inverse transform sampling, will work well for example, an exponential, a double exponential, or a Weibull distribution, but it will not be directly applicable for a gamma or a Gaussian distribution. So let's take a look at the example of a Gaussian distribution. The cumulative distribution function is well known, but the quantile function is only implicitly defined. As such, we don't have a closed formulation for the quantile function, for the inverse function, and so the only thing we can do is use an approximation of the quantile function up to an arbitrary precision. The better the precision that we can reach, of course, the better the generated random numbers will be. So here in green is the exact quantile function of the Gaussian distribution, and the blue dotted line is the approximation. So we see that it is pretty well for higher values, but for the lower values of u, there is a slight deviation.